Okay, so this is part 2 of the review video for circular motion and gravity. The last video cut off as I was talking about this problem, number 3 in your packet, that's looking for an expression, an algebraic expression for the magnitude and direction of the net force experienced by the planet. Well, the planet is moving in a circle. If it's moving in a circle, there's a net force that can be described as a centripetal force. And we have an expression or an equation for centripetal force. That being that F centripetal is just mv squared over r. What we're given, we need to use the variables that were given. Oops. And what was given to us was the mass of the planet, the speed that it's going around the planet, and this variable d, that's the distance the planet is from the sun. Now in this equation, we have this m that is always the mass of the object that's rotating, in this case the planet, so it matches the m that's given. This v is the tangential velocity, or the speed that the object's going as it's going in a circle. And instead of the d that matches what's given in the problem, we have an r in this original equation. And as I've said in the last video, this r doesn't just mean radius of a circle. This r represents something, and that thing that it represents is the distance between two objects that are the distance between the object that's going in a circle and the center of that circle. In this case, the center of the circle is the sun, and the object is a planet. They gave us that distance. They gave us this d, which is the distance from the planet to the sun. So rather than using r, we can just substitute a variable d in there. And this centripetal force is the net force, as we've been saying. And so it's just this mv squared over d. And that's one of the options. Option D. Actually, there's 2 of them. 3 of them. Okay. So the way we differentiate, so we know obviously process of elimination that this option A and E does not include mass. That's the thing that differentiates it from these 3. They're asking for the direction of the net force. A centripetal force always acts on the object inward towards the center of the circle. And so if we look at option D, along the orbital path, that can't be it. Option C, away from the sun, that can't be it. If it were accelerating away from the sun, then it would move away from the sun. But it's actually accelerating towards the sun with some tangential velocity that keeps it going forward. So even though it wants to go tangentially to this orbital, this circular path, this inward force keeps it from getting further away from the sun. So the answer is B. Moving on to number 4 on your packet. An astronaut lands on a planet whose mass and radius are each twice that of Earth. If the astronaut weighs 800 newtons on Earth, how much will he weigh on this planet? Well, this is a problem where we have to consider Newton's law of gravitation. And I'll go back here. Newton's law of gravitation mathematically is this, where the force of gravity is equal to some constant multiplied by the masses of the 2 objects and divided by the distance that separates these 2 objects squared. So if the problem is saying that the mass of the planet is doubled and the radius is doubled, let's see what that does to the original force. So let's say this is the force of gravity on Earth. Put a little e here. And the force of gravity on this new planet, I'll just use a prime, is g double the mass of Earth. The mass of the person stays the same, and the radius is also doubled. Ultimately, this gives us an expression where you have this 2 and a 4 in front of the exact same expression that we originally put, which was up here. This factor can go out in front, this factor gets squared, and I just put it out in front. So you have this original force that we had on Earth, except it's changed by a factor of 2/4 or 1/2. So the force of gravity on this new planet is actually just 1/2 that of Earth. Now they're telling us that this astronaut weighed 800 newtons on planet Earth. That's the force, and remember, weight is the force that gravity has on you. It's the force that you put on the scale on the ground. So on Earth, the man weighed this much. On this new planet, though, it has half the gravitational force on Earth. So if that planet is exerting half the amount of force that it does on this astronaut than he experiences on Earth, Newton's third law tells us that astronaut's going to have an equal and opposite force on the ground, on the planet. Then his new weight has to be half of his weight, his or her weight on this new planet than it was on Earth. So half of this astronaut's weight of half the weight that the astronaut experienced on Earth is what this astronaut's going to experience on this new planet. So the answer is 400 newtons. So the next problem in the packet asks, which of these planets would someone with mass m weigh the least on? It says 5 homogeneous planets have relative masses and size as shown in this figure. A body of mass m would weigh least on which planet? Newton's law of gravitation tells us that the force of gravity, so the force that any object, anything with mass, exerts on us is equal to this. This gravitational constant, which is always the same number. It's always 6.67 times 10 to the minus 11 units of newtons meters squared divided by kilograms squared. And then that number multiplied by the masses of the two objects, then divided by the distance that separates those objects squared. So we imagine this body M existing somewhere on the surface of one of these planets, and they mention that it's homogeneous planets, so we don't have to worry about the densities being different. It's equally dense everywhere. If we decrease the mass, like in this problem, like in this planet, planet 3, if we decrease the mass by taking half of the original amount, then, well, what's that going to do to the force of gravity on that planet? If we put a factor of 1/2 on this side, what's going to happen to the force of gravity? Well, the force of gravity is also going to go down by 1/2. So it's experiencing less gravity if the mass is decreased, and that's what this problem's looking for, is the least amount. And the size of the planet also matters to the force that gravity has on any object that's sitting on the surface. So this looks like, if we're looking at the relative sizes, it looks like there's two different sizes. There's the smaller size and the bigger size. So now we have to ask, well, what's the difference? Oh, okay, these have different masses. Will a larger radius give us a greater force of gravity, or will a smaller radius give us a greater force of gravity? There's an inverse square relationship between the force of gravity and the distance that separates them. This is called the inverse square law, or it's just an inverse square relationship, where if this gets increased, if I increase something in the denominator of this expression, the force of gravity will actually increase. So that relationship is telling me that if I'm looking for the planet with the least, that will decrease the amount of force of gravity acting on some mass that's sitting at the surface of the planet, then I want to increase the radius. So a bigger radius will give me a smaller force of gravity. So a bigger radius and a smaller mass will give me the least amount of gravitational force, and that's planet number 5. Okay, the next question asks, a satellite of mass m is in circular orbit about the Earth, which has a mass of capital M at a height h above the surface, where h is just the radius of the Earth, where h is actually just the same as the distance of the radius of the Earth. What velocity should this satellite have in order to maintain its orbit? So this is a problem where you have something orbiting Earth, going in a circle around Earth, maintaining that circular orbit, and the only force acting on that the satellite is the force of gravity. So centripetal force is equal to the force of gravity. Force of gravity, if we're not on Earth, remember we use this expression anytime we're outside of Earth, is this expression here. And centripetal force can be given as centripetal force is a net force that is equal to the mass of the object that's rotating times velocity of that object squared divided by the distance between that object and the center of the circle. So the net force is centripetal force because it's going in a circle, and the only thing acting on it is this force of gravity. So using Newton's second law, the sum of forces, there's only one force acting on it. And I could begin to use the variables that they gave. So there's the mass of the satellite, the mass of Earth, and the distance between Earth and the satellite. They said that the satellite is a height h above the Earth. And then that's the height above the Earth. So this is Earth. This is the center. So there's this radius r. And the satellite itself is going, let's say that's the satellite. It's this distance, this additional h distance. So this total distance that separates the satellite and Earth is just h plus r. And that's all squared. Don't forget that little square. The sum of the forces is mass times acceleration, and it's accelerating centripetally. It has centripetal acceleration, which is this v squared over r. But before I put that, actually let me think carefully. This is the mass of the satellite, because that's the thing that the forces are acting on. This is the velocity of the satellite. And then this r represents the distance of the satellite from the center of the circle, which is the same thing we used over here, this h plus r. And there's no square here, but the square is in the velocity. And the problem is asking for us to create an expression for the velocity of the satellite. So we're trying to solve for this v variable, this thing right here. So at this point we need to practice our algebra. And I won't talk through that, but I'll show you the final answer here. One thing else I want to say about this problem, because you get to a point where if you stop here and you look at the options, there's none of them have an h in there. So there's a point where you have to think, well, what was given to me, and what can I do with this h if there's another step I'm missing? And remember, they gave in the problem, they told us that this h is the same, coincidentally, the same distance as the distance from the center of the Earth to the surface of the Earth, or the radius of the Earth. So at some point, you have to substitute this h with an r, and that's what gives you this 2r at the bottom. It's really neat to see that the mass of the satellite, the lowercase m, isn't in our final answer, and that tells us that the mass of anything that's orbiting, anything that's in orbit around Earth or any planet, its mass doesn't matter when it comes to its speed, when it comes to its tangential velocity, which is kind of neat. Anything orbiting Earth is going to be going the same speed.